Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So in this video we discuss about chapter 2, capacitor and dielectric. I expect you guys already watched the introduction of capacitor video that I posted in Google Classroom as well as in ED Puzzle. So over there we discuss some of the ideas about what is capacitor, and there's some questions over there as well. So if you haven't watched that video, please watch that one first before you are watching this one. So I expect you guys have some general ideas about what is capacitor. Okay, so in this topic we can divide into three main subtopic: capacitance and capacitor in series and parallel. That one we will focus on this video, and then 2.2 and 2.3 we discuss in another video. So in this subtopic we discuss about capacitor, what is actually capacitance, capacitor where it has a series and parallel, and then charging is okay. That one is for the next subtopic. Okay, for the first subtopic you have to be able to define capacitance. This is the main general formula, and then derive and determine. So you need to be able to derive and then derive again and use energy stored in capacitor U. Okay, so capacitor is basically a device that can store electric charges or electric potential energy. Okay, it consists of two conducting plates separated by a small air gap or a thin insulator. That one is what we call a dielectric material. Okay, what is actually capacitance? It is actually measurement of the ability of capacitor to store charge. The higher the capacitance, you will expect to have higher ability to store charge. Like I told you before, the main formula is this one: C equals to Q over V, where this one is, I think, it's a little bit similar to the Ohm's law, where you have V equals to IR, but instead of that, here we have C equals to Q over V. Okay, here, if I rearrange in terms of Q, it will be Q equals to CV, since C is basically a constant, like R. And then I can write this one as Q directly proportional to V. Capacitance is a scalar quantity, and the unit that we use is farad. Okay, so like resistor as well, you have capacitors which is in series and in parallel. I think by now you should be able to differentiate between series and parallel. For series, basically you have capacitors sitting next to each other. Basically there's no junction between them. And for capacitor in parallel, you expect to have a junction between one and another capacitor. And as a rule of thumb, normally when I try to memorize how to calculate the effective capacitance of the series and parallel, I expect this one will be opposite to the one in the resistor. Okay, so I will expect a bit more, so don't worry. So now we're gonna learn about how to derive, how to calculate the C effective. Okay, so for series, maybe I can start to draw it over here. Series capacitor, sorry, it's capacitor in series, so maybe I can try to redraw it over here. Okay, how do you want to differentiate between a capacitor in series and capacitor in parallel? The key difference is actually, one, you have a junction between them, another one you don't have any junction. So in this case, in series, you can see that this one is actually, the capacitors are lined up next to each other. So in between them there's no junction, and similarly I can draw it like this. It still means that my capacitors are in series. Okay, I'm gonna erase that one. I can, so to show you the difference between capacitor in parallel, like in this case, okay, like this, you can see clearly there's a junction here and here, so this one is in parallel. Okay, and then I think maybe in exam they will give something that is more subtle, like, oops, something like this. Okay, this one is also considered as a parallel, because this one is actually you have a junction over here, here, and here. So if you want to differentiate between capacitors in series and parallel, there's the difference. So I'm going to erase first. I'm going to draw it properly after this. So back to the series. Maybe I can label this one as C1, C2, and C3. Okay, if you want to derive the formula for C effective, so basically I want to calculate the C effective, you have to know the properties of capacitors in series. So I will go into detail the mechanism of how capacitor works, like how the charge came in to the capacitor and how it fill up on one side, one plate, and then we push another parts to becomes positive and negative. I will show in details in the next subtopic lah, 2.2. But for now, I just want you guys to get some ideas, the properties here. So actually when the capacitor is connected to a battery or a potential difference, you will have electron coming up from the negative plates, like this. So this is the direction of electron, and at the same time, basically this is the direction of the charge. We are talking about C equals to Q over V, right? So I'm going to write C equals to Q over V over here. So you want to know what is the relation between C, Q, and V in series capacitor. So when you have charges moving in this direction, basically this charge, since there's no junction or anything, so all the charge will come in over here, and we start to push the charge into the next plate and the next one. So I can label this one as Q1, maybe I can label this one same with the capacitor instead. So this would be Q3, okay, Q2 and Q1. So this is not nice. Okay. So what I'm trying to say is that when the amount of charge is equivalent in this part, and I push to that part, and I push to that part, then you can write that Q1 is actually equals to Q2, and then equals to Q3. Okay, so this is the direction of the charge just now. The current will be in the opposite direction lah, in this case. But for now, you're going to ignore that one first. Okay. And then another important thing is about potential difference. Okay. So let's say if I have a potential of V, normally you can imagine that if this one is delta V, right? So this one would be my V1, this one will be my V2, and this one will be my V3. So the total potential difference is equivalent to V1 plus V2 plus V3. So maybe I can write V total ataupun V terminal. So I can just write VT over here equals to V1 plus V2 plus V3. And then if I rearrange this one, I can write this one as V equals to Q over C, right? So if I'm going to write this one as Q over C, it have to be the same subscript with this one lah. So it will be Q total over C effective equals to Q1 over C1 plus Q2 over C2 plus Q3 over C3. And since the properties here apply, where Q1 equals to Q2 equals to Q3 equals to Q total as well, so this one just becomes, I can cancel out the Q, all the Q's, and then I'm left with 1 over C effective over 1 over C1 plus 1 over C2 plus 1 over C3. Okay, ignore the background noise. Oops. Okay, so this is how you calculate the C effective. So if they ask you to derive, basically this is how you derive. Okay, and it could be the general formula would be like that. If you have more than 3 capacitors, then you just have to add all the capacitors 1 over 1 over 1 over, and the C effective basically 1 over those things. But let's say if you want, so but in the main, normally when you try to calculate things, you just have to use this one. You can ignore the derivation. You don't have to derive every single time lah. You can memorize this one straight away. Okay, another important things that I would like to point out is about our V, Q and C here. Our C equals to Q over here, V here. If you are using C1, this one will be Q1 over V1. Okay. I'm going to write it over here. So if I'm writing here as C1 equals to Q1 over V1, notice that the subscript will be the same. If C2, it will be Q2 over V2. For C effective, basically that one is just a total up. Then this will be Q total over over V terminal. Sometimes they use Q naught, sometimes they use Q total. It's basically the same thing. Maybe I can change to Q net instead. I have to check your notes. They just use Q and V. Okay, because I want to differentiate between without subscript and with subscript, I just write that one as, okay, I'll leave it in QT. Moving on, okay, now moving on to the parallel. So if I want to draw, maybe I can redraw like this. It becomes nicer. Okay, again, the key thing here is that you have a junction between the next capacitor. So that one indicates that the capacitor is in parallel. So it is connected to a battery as well. Okay. Now, let's say if I put this one as C1, C2, and C3. So if I want to calculate the C effective, the derivation would be like this lah. So I will derive the C effective for parallel. So let's say if the same case like before, you have charges moving in this direction, Q. Let's say I put this one as Q total, and then it came into a junction. So the thing about a charge, when it goes to a junction, it will try to separate. So example, if I have total Q total here is 10, so maybe it separates into 3, 3, and 4. So total up is still 10, but basically every time they goes to into junction, it might separate. Okay, the charge will try to go to the line where to the parts where you have the least amount of resistance. You can imagine that this one is like a car, so 5 cars going into the junction, so they will try to separate themselves. Okay, that's the idea. So in this case, instead of equal, I have Q total equals to Q1 plus Q2 plus Q3. Okay, so this is the first properties. And then the second one is about the potential difference. V total here, so you can see this one is the same lah. V3, V2, and V1 is the same value. Because it's basically across the same thing. Vt equals to V1. Oops. Okay. Correct. V1 equals to V2 equals to V3. So if I want to calculate the C effective here, I can start with the Q total. Maybe I'll just rewrite it again. And then since C equals to Q over V, I can rearrange Q equals to CV. So this will be C effective and V total CV equals to C1 V1 plus C2 V2 plus C3 V3. And I can cancel out all the V's because the V is the same in this case. So I'm left with C effective equals to C1 plus C2 plus C3. And then if you have more than 3, then just have to add. Okay, so this is how you calculate C effective for parallel. Okay, let's try to look at example. So this is how you calculate the total capacitance. So this is the example on how to calculate total capacitance. So for example 1a, you have capacitors in parallel. You can see that this one has a junction over here and over here. So C1, C2, C3 are parallel to each other. So how to calculate that one? You simply have to add 5 plus 10 plus 15. Don't forget the micro. So it will be 30 farad. 30 microfarad. For question B, so maybe I can write this one as C effective equals to 5 plus 10 plus 15. Okay, so in exam actually write times 10 to the power of 6, negative 6. For series, you can calculate using 1 over C effective is equals to 1 over 5 plus 1 over 10 plus 1 over 15. So you can see that there's no junction between them, so it will be like that. Okay, so you guys are using C. Okay. So now if you add, so this one becomes 3. Okay, so you have to press the calculator. I cannot count. Okay, so I'm going to press the calculator. So if you calculate, and then don't forget to do 1 over C effective so that you can get C effective. So the answer would be 2.7 times 10 negative 6. Okay, in this case, question C, you can see that there's a junction here. So basically you have to solve this part first. So I think by now you guys shouldn't have a problem with this. So solve this one first. Once you solve that one, you will have things like this. Okay, so this would be C12, and then this would be your C3. So this is the second step. For the first step, it is basically capacitors in parallel. So you just have to add those two. I'm going to write it over here. C12 is equals to C1 plus C2, because that one is in parallel. So it basically just 5 plus 10 micron, again times 10 negative 6. So this one is 15 microfarad. Okay. And the next step, you have to solve this one. So this is the first step. The second step, I can calculate this 1 over C effective is equals to 1 over C12 plus 1 over C3. This one is just 1 over 15 plus 1 over 15. So you will get 2 over 15, which is, if you invert that one, you get 7.5 times 10 negative 6. So this is how you calculate for example 1. For example 2, so normally in exam, the question will be something similar like this one, like example number 2. They ask you to calculate C effective first, or maybe indirectly you have to calculate the C effective first, and then only you can solve the next one. Okay, determine the potential difference across n charges on capacitor X and Y. So question 1 to find V and Q for capacitor X, Y, and Z. So Vx, Vy, Vz, Qx, Qy, and Qz. So normally, even before you read the question, you will expect the first thing that you have to do is that you have to calculate the C effective. So I can divide this into two parts. If I want to calculate C effective, I can divide this one into a capacitor in parallel, and then it is actually in series to the next one. So if I want to calculate CYZ, that one is in parallel. So CYZ is equals to CY plus CZ, where that one is just 1 plus 2 micron. So my CYZ is 3 times 10 negative 6 farad. And if I want to calculate x, y, z, which is my C effective, 1 over C x, y, z is equals to 1 over x plus 1 over y, z, which is 1 over 6, 1 over 3. So if I want to add, then it becomes 3 over 6. I invert that one, then it becomes 2. So basically this is your C effective. So I just recheck my calculation. 1 over 6 plus 1 over 3, it becomes 3 over 6. So 6 over 3 is okay. I think that one's correct. Okay, this is the first thing that you need to do. Second thing is that you have to take notice on the 12 volt here. So once I got the C effective, which is equals to 2 microfarad, then I can calculate. If I have V equals to 12 volt, I can calculate my Q. So that is V terminal, then I can get Q total. Okay, using C equals to Q over V. So my Q is actually CV. I just have to multiply, so I will get Q total is equals to 24, this one is micro, times 10 negative 6 coulomb. Charge is coulomb. What does that mean? Is that I have a total of 24 microcoulomb coming out from this direction. Okay, so you know that Q y z is equal to 24 microcoulomb, because you know this is the total, and at Qx is equals to 24 microcoulomb as well. But this one is for yz, not for y or z. It's a combination of those. So if you couldn't see, maybe I can redraw it over here. So this is my 24 microcoulomb. So this is my CYZ, and this one is CX. So obviously this one is QYZ is equals to 24 microcoulomb. Basically it's just total one, and this one is total as well. So I already have QX and CX. Now I can find my VX. My V is actually equals to Q over C (24 divided by 6), 4. Okay, volt. So in this 4 volts here actually means that I'll just redraw it over here, the one that I draw it over there. Okay, so 12 volt represent the total here. This one, the total from here to here is 12 volt. And you already calculate Vx to be in this one, which is equals to 4 volt. So the remaining one would be 4yz, which is equals to 12 minus 4, which is equals to 8 volt. Okay, so number 3, I'm going to write over here. So number 4 means step. I'm going to write over here. It is actually V, if I want to find V, Y, Z is equals to, okay, maybe I skip one step. Okay, V total is equals to Vx plus Vyz. So 12 equals to Vx is 4. We want to calculate Vyz, sorry. So I have to pretend I don't know this one. So Vyz is equals to 8 volts. So this is the steps on how to calculate. Oops. What did I press? Okay. So now I have 8 volt over there. I can redraw it like this. Okay. Let's change my pen color here. So that one, back to the initial diagram. Okay, the 8 volt. Okay, this one is 4 volt. Okay, the 8 volt actually represent this part because this one is parallel, so this one is the same 8 volt. Okay, so you have C over here, which is equals to 5 and 10. So if I want to calculate my I forget which one. Vy is about over there. Okay, saya salah tulis. Should be 1 and 2. Oh, that one's a different question, is it? So it will be 1 and 2. Okay, so I still forget to write. That one is Y and Z. Okay, this one is Y and this one is Z. Okay, now this is my fifth step. I can calculate the Q over there by using C equals to Q over V. So my Q is equals to CV. So if I want to calculate QY, then I have to use CY VY. So CY is 1 micron multiply my V, which is 8. So I get here is 8 times 10 negative 6 coulomb. QZ is equals to CZ VZ. So it will be 2 micro multiply with 8, which is 16 times 10 negative 6. And you can see here, oh, this one is Z. You can see that if I add up 8 plus 16, I will get 24, which is equivalent to the total charges coming into this direction. So it makes sense actually in that regards, because you can imagine 24 coulomb, microcoulomb coming in this direction, separate into 2 parts. One is 8 microcoulomb, other one is 16, and then combine back again, the total up is 24. It goes to the next one, that's why that at X is 24 coulomb, microcoulomb. So final answer, I suggest you to rewrite all the answer. So V1 Q1, V2 Q2, and V3 Q3. Q2 here is 16 times 10 negative 6 coulomb. Q, okay, I should use X, Y, Z. This one is Z, not, I thought that one is 2. So I'm going to have to erase everything. X, Y, and Z. Vx, okay, I start with Qz first. 16 times 10 negative 6 coulomb. 8 times 10 negative 6 coulomb. This one is 8 volt. This one is 8 volt. This one is 4 volt. And this one is actually 24. Okay, so you can always recheck then maybe you can try it again. Okay, so the last example that I will discuss before we go to energy store is this one. Okay, the question was to determine the effective capacitance of the configuration shown in figure below. All the capacitors are identical and each has a capacitance of 2 microfarad. So if you want to determine the effective capacitance in this kind of circuit, my suggestion is that you try to redraw the circuit. So can I copy this one? Okay, I couldn't copy this one. I can. I'll copy that one to the next page. So it's stated here that each one of the capacitance is 2 microfarad. So 2 microfarad. Okay, you can imagine if you want to redraw, maybe you can take one end and then you go through one by one. So let's say if I take this end, okay, bottom on the right here, point A. Let's say point A. So basically you want to go from A to B lah. So if you go out from A, the first thing that you'll see is a junction over here. Okay, what I will do is I want to draw differently. So this is my point A. Okay, go straight and then meet up a junction like that, and then it separates into two. First one and the second one. So if this one got subscript capacitors like C1, C2, C3, you have to write out which one is C1, C2. So in this case, you don't have to because it's basically the same. So you go here and then you go straight and then you went into this one. Okay. So this is my second junction. So I can draw it over here, my second junction. Okay, maybe I can use a different color now. So that one we separates into two, 1 and 2. Okay, so defeating the purpose of drawing the junction over there. So separates into two like that. So again it becomes another capacitor like that. And then actually this one just goes straight and meet up another capacitor. It doesn't go through any junction, so that one will be in series. This one will be in series as well, and then it goes back and then it meet up with the junction, the one from the below there. So yeah, it should be like that. Okay, change one more color. So ignore this one first. Try to do the one that we drew just now. So bottom there, maybe I can draw in a green line. So back to the first junction. This one is my green. This is the green part. Okay, and then go straight, and then supposedly we meet up with the last capacitor. So I have to hold on for that one. I'm gonna do this one. So it goes out from the, oops, I cannot see, change to a bit. Okay, hopefully you can differentiate between red and orange. So from that junction, it go through a capacitor, this one. Okay, and then it meet up with the green one just now. So the color that I choose is just to, differentiate between those and those. In exam, you can do a different color as well if you want to. It might help, especially in the next chapter where you have Kirchhoff rule. Okay, now if you're looking at this one, for me personally, I found that this one is much easier to understand or to calculate. Okay, the first thing I would do is I would like to solve above here first. I have the one in series, so I can simplify that one. just becomes like that, and goes back to here and goes out again. So okay, if I want to calculate that one, I can use, because that one is in series, I can use 1 over C effective for that one is equals to 1 over 2 plus 1 over 2 plus 1 over 2, because this one is 2 micron each. Okay, so half, it becomes 3 over 2. So my C effective here is actually equals to 2 over 3. Okay, so I suggest you to use a calculator instead, because some students, they might get confused. Okay, take a calculator. 1 over 2 micro. Okay, 2 exponent negative 6, 1 over that one. Okay, so I will get here is 6.67. Farad. Okay, that one is over here, the top one there. Okay, for the next one, maybe I can combine this two. Okay, so now I want to combine this one. This one just in series, parallel, so you can calculate straight away. So it will be C effective for that one would be equals to 6.67 times 10 negative 7 plus 2 times 10 negative 6. So here I got 2.667. I think I might have to recheck my calculation. Okay, just want to recheck my calculation up there. Okay, correct. So you add what with the okay, I think so far everything is okay. Okay, now once you combine those, basically what you will have is something like this. Now it will become more simpler. So in exam you can do it like this. Okay, obviously you can do once combine straight away, but I strongly suggest you to use this method one by one. Okay, so now I have 2.67 over here. Okay, I just draw an arrow there. So okay, so this is my initial one, this is my second step. Okay, if I have 2.67 over there, I want to calculate all these three. So this 3 is in series, means that I can calculate using 1 over C effective equals to 1 over 2 micron plus 1 over 2.67 micron plus 1 over 2 micron. So obviously you have to write times 10 negative 6, but because I'm running out of space, so I'm doing it like that. 1 over 2 exponent negative, okay, 2 exponent negative 6, 1 over 2.67 exponent negative 6 divided by that one I got here is 7.28 times 10 negative 7 farad. And now on to the last one. Okay, because that one is simply 2 capacitor now in parallel, so this one is for that one. So the last one is the easiest part. C effective for the circuit would be 7.28 times 10 negative 7 plus 2 times 10 negative 6 for it. So here I get 2.0. Okay, saya salah tekan 7.28 negative 7 plus 2 exponent negative 6. 2.73 times 10 negative 6 farad. Okay, so again, I just repeat, if you have this kind of question, the first thing you want to do is you try to simplify the easiest one. In this case, I simplify the top here, the 3 two. I combine. That one is in series, so I have to use 1 over per. So 1 over 1 over 1 over. And then next one, I combine the next one and next one and next one. But before you start combining those capacitor, I strongly suggest you to redraw the diagram. In terms of it might help you to understand the circuit better. So final answer here, they get 2.73 micron, which is exactly the same with ours. So yeah. Okay, example number 4, you might have to go through yourself. Okay, energy stored in a charged capacitor. When the switch in the circuit closed, charge begin to accumulate on the plates. So this is what happens when you close a switch. Basically, the circuit is complete and the current is running. A small amount of work is done in bringing a small amount of charge from the battery to the capacitor. This is given by, so amount of work is equal to V delta Q, change in charges, and V equals to Q over C. So I can write this one as dW equals to Q over C dQ. Okay, so if you guys still remember in advanced, if you have dW, you want to get W, you have to integrate. So this is the first one. In your learning outcome, you need to be able to derive. So if you want to derive, you can start from here. So this one just integration of 1, so that one become W. Since W is equals to U, you can replace U. So actually you get W over here from this integration, and then since W is equals to U, you can write it U equals to on the right hand side. So for this one, if I want to integrate, it will be Q. This one is to the power of 1, so you have to add 1 because Q to the power of 2. Okay, and then you bring the one that you add to the front below here, so it becomes like that. So you have 1 over 2 Q squared over C. So if I want to rearrange, and then I can substitute back the, in this case, if I substitute Q equals to CV, so I have here is C square V square. I can cancel out the C square, C square, and then I end up with U equals to half CV square. So normally, most of the time, I prefer to use this one, but again, it depends on the information given. You can always choose what best for the question. Okay, maybe you can discuss one example. Okay, the figure shows a combination of 3 capacitors where C1, C2, C3 is connected to the combination. Determine the effective capacitance of the circuit. So you have this kind of circuit. First thing you solve is that one, the one inside the box, C2 and C3, which is in series. If you want to calculate, you have to use 1 over C2 plus 1 over C3. So I'm going to go through that. So you get here C23 equals to 15 microfarad. So if I want to redraw that one to the one that we drew, so you will look something like this. So just redraw a little bit to make it easier to understand. So up here you get a total of 15 microfarad. So if you add up with that one, which is equals to C1 is 100, so you have 115 microfarad for C effective. So this one, you just have to add. Okay. And then see the capacitor. Okay. So if you are talking about properties of C and V, then looking back at this, where's my diagram? Looking back at this diagram, you can calculate the Q naught first. So you already have C effective, which is 115 microfarad. Okay, 20 volt is given, that was V terminal, which is 20 volt. Now you can calculate the Q total, which is equals to C equals to Q over V. Q equals to C multiplied by V, which is basically 1.15 multiplied by 20. Okay, I'm gonna write it properly. Just double check the value 115. Okay, 115 exponent negative 6 multiplied with 20. I got 2.3 times 10 negative 3. Okay, that one is the charge coming out from this direction, from the terminal. It goes into here, it basically split into two. Okay, one more criteria that is important is here is 12 volt. Is it 12 volt? Okay. 20 volt, sorry. So this one is 20 volt. So over here, I will have 20 volt across here. This one also 20 volt. So here is written like that, 20 volt. And then you calculate Q1 by using, you already have all the values of C1 and V1. You calculate C1. Once you get that one, again you can, this one you can calculate the Q easily, the first one. For these two, okay, if you already have Q1 over here, I can calculate the charge over there. So I have how many charges are there? Total Q naught, Q total is 2.3 times 10 negative 3. So that one, if it goes into here, it can separate into two parts. So you minus with Q1, you get the whatever charge left to go through that part. So this is what they do. Total charge, we already show how to calculate. And this one, just show over here. Okay, you can imagine that the charge going into this direction is 2300 microcoulomb. Okay, charge at Q1, the one that we already calculate, is 2000 microcoulomb. So you expect the rest will go in this direction, which is 300 microcoulomb. So this is how you try to do. If you draw it properly, then shouldn't be a problem at all. Okay, the charge over here and over here is the same because there's no junction between them. So straight away you can calculate the potential over there. Okay, so here they calculate V2 equals 30.6 and V2 equals 30.3. The question actually want you to find across C2 only. Okay, effective we already calculate. Potential difference we already calculate. Now we want to calculate the energy stored in capacitor C3. So this one is Q1. Charge stored is Q1. The energy stored, okay, this one we already answered that one, B. The energy stored in the capacitor C3, and then the area of each plate, the distance. Okay, the last part I'm going to ignore first because that one is from the last subtopic, so I ignore this one, 2.3. I'm not going to touch that one. So if you want to calculate, so this is for this chapter lah. You can use whatever formula that you want. So we have U equals to half CV squared or U equals to half QV. U equals to half CV squared. Maybe I can use this one to compare the difference. So this question I want to find at C3. You already have the C. Did you calculate the V? No, I don't think so. Okay, that since there's no V, maybe we can use a different formula, which is equals to half QV. Ni tadi. Okay, so if I want to use U3 equals to half Q3 V3, I just have to substitute the value. So this one is 300 times 10 negative 6. Okay, so again, I don't have the V. Okay, no wonder they are using that formula. Okay, this one is U. Okay, if I want to replace the V, I can use C equals to Q over V. So my V is equals to Q over C. I can substitute inside here. So I got U equals to half C Q square over C square, because the square there. So cancel out that one, you left with U equals to Q square over C. So using this particular formula, I can substitute the value, I should get U3. So that's how you calculate the energy stored. So normally in exam, something similar like this. They ask you to calculate energy stored after you have all the information to calculate this. And then, okay, so I think that's all for today's video. We continue the next one for subtopic 2.2. So I'm going to put this one as our end here. Okay. Yeah, I'm not sure what I'm going to return over here. So this is for end of part 1. End of part 2 lah. Okay. Thank you.